started then. Okay, so today I'm very pleased to be able to introduce Jonathan Stern. Jonathan got his PhD in CITA, working at Mary Leor, and he's currently a postdoc at NPIA in Heidelberg, so in Luxembourg. And he's done a lot of really nice work on the properties of gas associated with quasar outflows, quasar emission lines, etc. And today he's going to talk about his latest. Go ahead.
Okay, guys, thanks for coming. I'm going to try to use my time to present two subjects that I'm working on. So the first is, I should use this or my hand, probably best. Yeah. So the first subject is AGN-driven galactic winds, so that's related to quasar feedback. And the second subject discusses the circumgalactic medium, this gas which is beyond the galaxy's stellar body, but still associated with the halo of the galaxy. And of course, this work could not have been done without a pretty long list of collaborators. So both in Germany, in the US, and also where I did my PhD in Israel. Okay, so let's start. So first, AGN-driven galactic winds. Why should we be interested in these winds? So they potentially provide a mechanism for the quasar to regulate star formation in the host galaxy. And this coupling between the growth of the black hole and the growth of the galaxy may explain these very well-known relations between the black hole mass and the properties of the bulge. So that's one reason. Another reason we're interested is that structure formation simulations require some mechanism to shut down star formation in the most massive halos. So these winds are a leading candidate to be this mechanism. Okay, so how can a quasar accelerate a wind on a galaxy scale? So when I say galaxy scale, I mean kiloparsec scale outflow. So several mechanisms for the acceleration have been proposed. I'm showing you here two. We can discuss more if you want at the end. In this first model, okay, the quasar launches a nuclear scale wind. Okay, so these are the winds that we see as broad absorption lines, for example, in the spectra of quasar. When these winds reach the ISM of the host galaxy, they shock. Okay, they interact with the ISM and they shock. They create a hot gas bubble. And then this hot gas bubble expands and pushes on the ISM, creating a galaxy scale outflow. So this is one possibility. Another possibility is that radiation pressure directly from the quasar pushes on the ISM and creates a galaxy scale outflow or wind. So what I want to show you in this part of my talk, okay, I want to present an observable of these winds, which can be used to distinguish between these two scenarios. Okay, and the observable is the pressure of the 10 to the 4K gas. Okay, so the 10 to the 4K gas is the gas which is exposed to the AGN radiation and emits the emission lines that we see in quasar spectra. Okay, so we can use these emission lines to constrain the pressure of the cool gas. So what do we expect for the cool gas pressure to be in each one of these scenarios? In this scenario, okay, it makes sense that as long as the gas is beyond the shock radius of the nuclear wind, we might expect the cool gas to be roughly in pressure equilibrium with the hot gas. Okay, that makes sense if, for example, the cool gas is created from instabilities in the hot gas, or the cool gas is ISM gas, which survived after the shock went through and compressed it. So that's in this case, okay? But what do we expect for the cool gas in this case, okay? In this radiation pressure dominated case. So to get a feeling of what happens in this case, we ran this RHD simulation, radiative hydrodynamic simulation. It's a simple setup. We start with a spherical cloud, which is very optically thick to the UV radiation. And then at t equals 0, we turn on the AGN radiation. Okay. After 10 to the 4 years, okay, the cloud looks like this. okay, you can see, oh, so the radiation is coming from below. You can see that the radiation has compressed the surface layer of the cloud. Now, if you are familiar with solutions to dynamic H2 regions, this is a very different solution than the standard solution. In standard solution, when you turn the source of ionizing photons on, the surface layer of the cloud heats up, okay? And then because it's overpressurized, it expands towards the source of radiation. Okay? The difference is that in this, in the standard solution, radiation pressure is entirely neglected. Okay? While here, radiation pressure is assumed to be much larger than the gas pressure. So instead of the surface layer expanding, it's being compressed against the backside of the cloud. Okay? And of course, from the sides, you get ablation by the radiation ablation of the cloud. So in this case, it's exceptionally easy. You do the first interaction with ray tracing. So that's a UV photon coming. A UV photon turns mainly into an infrared photon. Okay? And for the infrared, the cloud is almost optically thin. Okay? So we handle the infrared with the FLD approximation, but it doesn't really make a difference because essentially the infrared photons are lost from the system. Okay. Okay. So let's see what we get. So let's take a look at the surface area. Right. This is the surface area which is absorbing most of the energy, most of the optical and UV energy. So this is also what's emitting the emission lines. If we take a closer zoom in on it, okay, we can see that there's a very strong density gradient in this layer. Okay, you have here a very low density layer, and above it a higher density layer. Even closer look shows you this graph. So here I'm plotting the gas pressure profile as a function of optical UV depth. And each gray line, can you see the gray lines? Each gray line is a radial skewer through the simulation. Okay, so radial in this figure is just the y-axis. Okay, so each gray line is a different radial skewer. When you look, the thick black line is simply the solution to the hydrostatic equilibrium equation. Okay, so it's simply the gas pressure gets a pressure gradient to counteract the force of the radiation. Okay. So the point here is just to say that if you look at the surface layer, okay, most of it looks like simply the hydrostatic solution to it looks like the hydrostatic solution. Okay. 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 So the conclusion from this exercise is that in order to calculate the emission lines that we expect from clouds under strong radiation pressure, we don't need to do a very expensive RHD simulation, okay, a CPU extensive simulation. Okay, we can simply assume that the emission line which dominates, sorry, the surface layer which dominates the emission of the emission lines, okay, is roughly in hydrostatic equilibrium with the radiation. Okay, and then we can calculate the solution to the radiation transfer problem very accurately with a static code such as cloudy. Okay? So this is what we do. Okay, so essentially we just calculate a static solution. You can see here that at the low optical depth you get very low density gas, so the oxygen is very highly ionized. And as you're going increasing in optical depth, okay, the oxygen ionization level is decreasing. Okay, it's simply because of this density gradient here, where the surface is very low density, and as you're going inside, the density is increasing. Okay, questions?
So the absorption of the UV photons is dominated by
Dust.
dust.
Yeah, the opacity of the dust. Yeah.
Your ionization parameter is probably pretty high.
So here it's very high.
So if you have a
It goes to infinity essentially.
yeah, well then it's all dust. But farther down, the ionization parameters are dropping. Not even competitive between oxygen, hydrogen energy and dust.
Even in the O3, it's still dust which is dominating. Only once you absorb like a significant fraction of the photons, only then it will become more significant. And then the gas will absorb all the photons.
Of course, it's the ionizing photons that provide the line emission. So what fraction of the radiation goes into that as opposed to being doesn't?
20%, roughly.
So
Yeah. Yeah, FF, yeah.
not negligible.
Yeah. It's not negligible. That's essentially why the neuroline region is relatively weak, okay, despite that it has a loud covering factor. Yeah.
Did you do the exercise of just taking those same skewers and running cloudy on a bunch of those?
Yes, yes. So essentially, when I say that most of the radial skewers look like this, it's essentially I'm weighting this by the amount of emission that each one is doing. Yeah, yeah. But you can.
What I'm asking is, did you do cloudy runs where you just took the density that you got through those skewers and put that in the cloud?
No. That I mean, you're saying just say like do a distribution of pressure profiles according to what we find, and then say, just compare it to the. Yeah. Okay. It should be similar to just use, but yeah. Okay. I'll check that. Yeah.
Would you assume perfect coupling of gas and gas?
Yes. Yes. The dust is very.
Within some reason, gas may drift into
Yeah, but the dust. When it's exposed to AGN radiation, the dust becomes very ionized. Okay, so the Coulomb coupling to the gas is very strong. Okay, so you get actually Bruce Drain did this calculation, and so in the lowest density layers you get some drift. Okay, but once you're here and the density becomes significant, the drift is entirely negligible. Yeah. More questions? Okay. Okay, so just a comment. These solutions, which are called radiation pressure confinement. Okay, so these are hydrostatic solutions to H2 layers. They've been addressed by several papers, both in AGN, Pierre and Voigt, Mactopita, and also in star forming regions. Eric Pellegrini, Bruce Drain did some work, and also here, Christopher Matzner and his student Cherrier did some work on these type of solutions. Okay, so our assumptions as follows. I'm going to calculate these hydrostatic solutions to the photoionized gas. In this case, I'm going to assume that the cool gas simply has the same pressure as the hot gas. And in this case, I'm going to use these RPC solutions where the cool gas is in pressure equilibrium with the radiation. Okay. Okay, so this is the comparison. This is the actual comparison with the observations. You have the blue lines are the predictions of this emission line ratio, this neon line ratio, using these hydrostatic photoionization solutions. The x-axis here is the ratio of the hot gas pressure to the radiation pressure. Okay, so this is the parameter of the models that we want to constrain. And the gray bars are the observations. Okay? So we're doing a direct comparison between the models and the observed emission lines. And you can see, okay, you can see here, right, you can see that the observations are consistent with the radiation pressure confinement regime. Okay, so the observations are suggesting that radiation pressure is much stronger than the hot gas pressure.
What are the solutions of family of?
So this is one parameter of the model. There's more parameters: the metallicity of the gas, the spectral slope of the incident radiation. For our purposes, these are all nuisance parameters. Okay, so that's just the different lines. Okay. So you can see that all solutions where the hot gas pressure is above roughly 5 times the radiation pressure are totally ruled out. Okay, so we get a hard upper limit on the hot gas pressure. Okay. Now there's no way to, this hot gas that's been postulated in this model, right, there's no direct way to observe it. It doesn't radiate directly. So the only way to view it is using like indirect methods like this. Okay, so essentially we're putting, let's say, a first upper limit on the pressure of the hot gas.
What? Ways are you typically coding?
Okay, so that's exactly my next slide. So the panel I showed you before is this panel. The nice thing about AGN is that you have emission from different distances. Okay, so you have emission lines coming which are resolved, okay, and they're coming from distances of between 1 and 10 kiloparsec. You have narrow lines which are between, this is what I showed you before, between unresolved, so they're roughly 10 parsec to 1 kiloparsec. You have clouds in the TOS, so these are expected to be roughly on 10 parsec scale. And you have clouds which are broadline region clouds. So these clouds, they have very wide velocities. They're very close to a black hole. They're on sub-parsec scale. Okay? So this is a very nice thing about AGN. Okay, you get emission lines from 4 orders of magnitude in distance from the central black hole. And you can see that in all cases, okay, the observations are consistent with the radiation pressure dominated scenario. Okay? So it's a very clean result, I'd say. We're going, right, so we're increasing 4 or 5 orders of magnitude in distance. Okay, that means that the radiation pressure is dropping by 10 orders of magnitude, but still it's the dominant source of pressure on these clouds.
So both the hot and the radiation pressure drop like 1 over r squared. So.
Yeah, okay, yeah. Okay. Okay, so are we done, right? Did we solve the problem and we can say it's radiation pressure and go home? So not entirely. The line ratios that we use, okay, they constrain the instantaneous accelerating force, okay, the force that we're looking at now, and that we said that it's likely radiation pressure. But we have another observable of these winds, and that is the momentum outflow rate. Okay? So the momentum outflow is, of course, the integration of the accelerating force. And then the momentum outflow rate is simply the time average force. Okay? Now, many studies have measured the momentum outflow rate in these winds. And you can see that the values that they get are between, say, 10 and 30 times L over C. Okay? So these studies led by Nadia Zakamska and Jenny Green and Nachum Arav. Okay, so why is this a problem? Why is it a problem that the momentum outflow rates are so high? The reason is that if we assume that radiation pressure is doing all the accelerating, okay, then the maximum momentum outflow that we can get is 1 time L over C. Okay, so this is much below the total momentum outflow rate that we see. So this is in the, do you see? Okay, so think about it. If you have radiation pressure, okay, that's the maximum momentum rate that you can get is L over C. That's assuming you have an outflow with 4 pi covering and a large optical depth. Okay?
The caveat I'd say is, of course, those are not measurements of the mass outflow rates or momentum outflows, because they can't get the mass outflow rate.
Yeah, so they're estimates, you're saying. Yeah, okay.
So, I mean, I would have agreed with this plot being more believable before your result.
Okay.
But given that the hot gas pressure just isn't there, you've got to pack a lot into some very small fraction of time.
Yes, yeah. So
I disbelieve this more than
okay, yeah. So there's actually been claims that all these measurements are overestimated. Actually, one paper claiming that came out just this Monday. So maybe all these values should be much lower. The other option, like Norm says, is just that you have to accelerate these winds in the past. Okay, and now we're just viewing them cruising under radiation pressure, but there was some stronger acceleration mechanism in the past. So that's the only if you take these results at face value, that's the conclusion that you arrive to. Okay?
Now, these clouds are mainly ionized, so when you measure the line strengths and you assume some metallicity, I guess there's some uncertainty about metallicity perhaps.
Yeah.
But given metallicity, you know what the hydrogen column is, and therefore you know the line width, and so you have some estimate of the velocity, and that's what gives you the mass flux.
Yes.
Okay.
Yeah.
So
the hard thing to do is to getting the radius is not trivial, right? So Nahum Marab has done a few of these points, like a handful.
Yeah.
If it gets the radius, you're looking at excited line transit, excited level transitions, so then you get an actual density. Most of the rest of them, they don't really know very so we get a factor of 10, which makes the mass loss rate vary by a factor of 1.
In some cases, it's emission lines, and then they claim they resolve it. But that's the claim, yeah. That's been contested, yeah. Okay. Okay, I should just note that this is the limit of radiation pressure and the single scattering limit. If you allow for some multiple scattering of the IR photons, then maybe you can push this up by a little bit, but probably not by enough. So the conclusion from this is either that everything here is overestimated, or that there was some previous phase where the black hole was not observable as a quasar, the accreting black hole was not observable as a crater, where the acceleration took place. Okay. Okay, I'll just flash that these kinds of solutions, radiation pressure confinement, also explain some open problems in AGN analysis. So one is that we see this overlap between X-ray and O3. So this can be explained because we have the radiation pressure creates this density gradient where the low density emits the X-ray and the high density stuff emits the O3. It also provides a solution to the Baal over-ionization problem because the radiation pressure essentially compresses the gas, so it creates a small filling factor for the Baals. Also, there's these outflows called worm absorbers that we view in the spectra, in the X-ray spectra of AGN, and they show a huge range in ionization between here you see iron 9 up to iron 26. And again, this range of ionization is explained with this density gradient of the hydrostatic solution. Okay. Okay, so that's the end of my first part. Questions?
So, can radiation pressure explain how much of fast outflows that people observe about 1% passivity?
Yeah, the ultra-fast outflows, I mean, the density structure that you derive is not consistent with this solution. So it seems that that's not something that's compressed by these radiation pressure. I mean, they could be accelerated by radiation pressure, but the solution is the compression of the gas radiation pressure, and it seems that it's inconsistent.
So one more point. So radiation pressure here is produced by the photon absorption of gas.
Yeah.
I wonder what
Or
is-
dust.
Or dust?
Yeah.
What is the effect of dust absorption? It contributes like 1% or 10% of radiation pressure?
Sorry, I missed the question.
So what is
He
the
says it's 4/5.
Oh,
Remember he said the hydrogen ionization only accounts for 20%. So the dust is
So the dust is 80%. Of course, that's only in cases where you have dust, which is in these three cases. In the broad eye region, there is no dust because you're within the sublimation radius of the gas. So here, the opacity is dominated mainly by line and edges. Yeah.
And there's no known mechanism for producing the ultra-fast absorber.
Yeah.
And I don't believe those results. They're low signal to noise, and the harder you look at them, the more they go away.
Yeah, they remain 2 sigma always, despite they're increasing the observing time. Yeah. It's impressive. Yeah. Yeah. More questions? Okay. So I'll go to the second part.
Well, I guess the
Yeah.
last question.
Yeah.
What's the covering fraction of these files? I mean, radiation pressure confinement seems to work if the covering fraction is modest but not very high.
No, it works for zero covering production. He's talking about radiation pressure gradient in a given cloud.
Well, that's fine. Yeah. It's modest. It's low to modest. That's fine. I'll break then basically because the covering factor is less than.
No, it doesn't matter what covering factor. All he's saying is you expose gas to radiation, you'll get this effect. It doesn't matter whether it covers the whole sky or there's an individual cloud.
It has to be optically thick, right?
Optically thick and one edge.
But if the covering factor in the near regions is 1,
Yeah.
then there will be no exposure.
Yes, exactly.
So you wouldn't see the quasar.
Yeah. It's only stuff which is exposed to the.
Self-selection.
Yeah. But to answer the question, roughly 50% of the AGN sky is covered by optically thick gas. Okay, so Yeah. The nice thing is that this 50% is distributed over such a large range of distances from the black hole. Okay. Okay, part 2. The circumgalactic medium. This is my very bad picture of the circumgalactic medium. We have, okay, so as I said before, the circumgalactic medium is this gas which surrounds the galaxy. It's beyond the stellar body, but still associated with the halo, so roughly 100 kiloparsec scale. Why should you be interested in the CGM? Because if you want to understand how galaxies accrete from the IGM, or alternatively, how the galaxies enrich the IGM, okay, in both cases, these processes go through the CGM. Okay, so observing the CGM gives you constraint on galaxy accretion and IGM enrichment. And how do we observe this CGM? I'm sorry if you can't see, if it's too low. It's okay. Okay, so this is one popular way to do this observation. You take a galaxy quasar pair, a projected pair, okay, so they're near on the sky, such that the line of sight of the quasar passes roughly 100 kiloparsec from the galaxy. And then you look for absorption features at the same redshift of the galaxy. Okay, so these absorption features likely come from gas in the CGM of the foreground galaxy. Okay, so what I want to do in this part of my talk, I want to build a new phenomenological model for the CGM. So first I want to argue that this phenomenological model is supported by the observations. Then I'm going to use observations to constrain the three parameters of this model. And then I'll discuss what are the implied CGM properties. Okay. Okay, so what do observations tell us about how the CGM structure looks like? So this is what you see here are absorption features from a single galaxy. Okay, so from the line of sight of a single galaxy. This is the velocity here is the difference between the velocity and the velocity of the galaxy. And you can see that there's a very large range of ionization states from magnesium-2, silicon-2, aluminum-2, and up to carbon-4, nitrogen-5, and O6. Okay, so you have a very large range of ionization states of the gas. And that already tells you that the gas is multi-phase. Okay? There isn't one density that you can use which gives you all these ionization states together. Yeah. Another thing that you can see is that the different phases are kinematically aligned. Okay, you can see that where the O6 has a trough, okay, then even magnesium-2 has a trough at the same velocities. Okay, so there seems to be some correlation. It's not a perfect correlation between the kinematics of the highly ionized phases and the lowly ionized phases. That's the second clue. And the third clue is that the size of the cloud tends to increase with ionization level. Okay, this is a measurement by Rob Simco. You can see that the sizes of carbon-4 and silicon-4 tend to be around 1 kiloparsec, while the size of the cloud, iron-2, magnesium-2, tend to be tens of parsecs. Okay.
You should explain these are two background quasar sightlines, right?
So this is actually from a single. So this is from a single sightline. He fit individual components. He derived the column. He used a modeling to derive the column. He got the density. Yeah, in line sight. Okay, so we get this relation that as the ionization level is decreasing, the size is also decreasing. Okay, but this is indeed, there's been additional support for these for this result using IonCoherent Scale measurements. So this is what Norm was referring to. You look at lensed quasars, you have multiple sightlines, and you look at the same absorption feature in both sightlines as a function of the transverse distance between the sightlines. Okay, and when one absorption feature starts to change compared to the other, okay, then you can tell that you're roughly at the scale of the cloud. Okay, so that's called an IonCoherent Scale measurement. So they get roughly the same results. Again, that's carbon-4 get a kiloparsec scale cloud, iron-2 and the magnesium 2 tens of parsecs. Okay, so let me continue. Okay, so we have these 3 clues for how the CGM behaves, and we built a new phenomenological model for the CGM. It's called a hierarchical cool CGM. It's cool because, again, we're assuming that all the gas is photoionized. Okay, it's all roughly 10 to the 4K, photoionized by the UV background. And this is a single cloud in this model. Can you see you see that the outer layer is very, very low density. The mean density is only 50 times the cosmic mean. And inside this low density cloud, you have pockets of higher density clouds. Inside each pocket, there's pockets of even denser clouds. Okay, so you have this hierarchical structure where density, the densest phases are in smaller and smaller clouds. Okay. Okay, what are the 3 parameters of this model? So one is that the size, what is the relation between size and density? And the second 3 parameter is what is the number density of the cloud. So how many clouds like this we have in the CGM, and within each low density cloud, how many high density clouds do we have? Okay. So just to make sure you guys understood what I'm trying to do, okay, I have a set of absorption line measurements of absorption lines. I'm going to model these absorption lines, assuming that the CGM has the structure like this, has this hierarchical structure, and then I'm going to derive the properties of the CGM.
R is the radius of the whole cloud. What is R?
Yeah, the capital R is the distance from the center of the galaxy. So small r is the size of each cloud. So I'm just going to I'm going to assume my CGM is spherically symmetric, and I'm allowing the number density of clouds to vary as a function of distance. Okay. You can also add like phi here if you're something disk CGM or. Okay. Okay, so the methodology is like this. Okay, you measure your sample, you choose a sample of galaxy quasar pairs, you measure the CGM absorption lines on it. Okay, then the tricky part is, it's relatively straightforward to understand as a function of these 2 parameters what are the absorption lines that we expect. But the tricky part is to reverse this function. This is what we do in the paper. I won't get into this now. And then we best fit these 2 free parameters, and we create a realization of the CGM based on these 3 parameters. Okay. Questions? Okay, so these are the fits. Essentially, we took a sample called Cos Halos, low redshift L-star galaxies, 44 objects, so 44 galaxy quasar pairs. What you see here in each panel is a different ion. The arrow bars are measurements of each object, and the gray lines are the fit of our best fit model. Okay. Okay. So we use all these observations. There are 600 observations here in order to constrain the 2 free parameters of our model. Okay.
So small chi-square doesn't mean that we have anything.
Small chi-square means we have a relatively good fit.
You showed the chi-square equals 0 and chi-square.
Yeah, okay, so in sulfur 2 we only have upper limits, so it's relatively easy to get a 0 chi-square. Yeah. It's still not trivial. I mean, not every model, some of the models would not fit with these upper limits. Okay, so there is some information in the upper limits. Of course, when you have much more observations, like in 06, then the chi-square is a bit off. But you have here 40 observations, and the chi-square is roughly 44. Okay, so it's a pretty good fit. So just to emphasize, it's not trivial at all that we could get a good fit using this model. Okay, there's lots of possible observations which would not yield a good fit. Okay, and from this, we can create our CGM realization. Okay, so we create a 3D model of how the gas in the CGM looks like. What you see here, okay, is a projected picture. Okay, so think about that the quasar is behind the screen, and the color is the maximum gas density along the line of sight. So in our CGM, the gas spans 4 orders of magnitude in density. Okay, the largest cloud size is 35 kiloparsec. The smallest cloud size is a factor almost 4 orders of magnitude lower, so 6 parsec. The area filling factor drops roughly logarithmically with density, but the volume filling factor drops more strongly with density. Okay, so the point is that we derive a picture of the CGM, a 3D model of the CGM. I think we're the first who managed to derive such a picture. And like I said, this is everything here is photoionized gas. There's no collisionally ionized gas component.
So in your model here, it looks like you've just got 2 cloud sizes, the small cloud and large cloud. Is that right, or do you have intermediate cloud sizes?
Yeah, so I think the middle, yeah, you can't see them. So in the main plot, I'm showing the 3 low density phases. I think you can't make out, no, you can't, hardly. You can make out the middle phase. But here, this is a zoom in into one of the middle cloud.
It's really tiny here.
Yeah, it's really, really tiny.
So for your model then, for the cloud size, is it basically just like a three possible radii, or do you have like a functional form that allows the clouds to be any kind of size?
Essentially, the model is continuous. Okay, I did. Yeah, it's a power law. Essentially, the size decreases as the density to the -1, roughly. That's what we get from the best fit. It's just for visualization purposes, I divided it into 5 phases, which differ by a factor of 10 in density. Does that answer your question?
I guess the gradients must be very steep. It's not quite clear why all the visualized clouds are all basically of 2 or 3 sizes. But I guess I have a slightly different.
The densities.
Okay.
Yeah, exactly. Yeah.
And do you also allow for small clouds outside of larger clouds? In other words, your hierarchical structure would indicate correlations with higher density things are within a larger higher density. Do you have like small high density knots populating low density?
Yeah, we don't allow for that, and the data supports that, because when you see the low ions, you're always seeing the O6 and the high ions. Okay, not necessarily. You can see only the O6 clouds, but not any low ion absorption or the other one. So it looks like, so that's actually one reason why we came up with this hierarchical model. Yeah.
So like if I understand this, everything's embedded inside everything else. So on the red circles, the scale I'm picking out is sort of the largest radius for O6, for example.
Yeah.
And there's other O6 clouds in there, but they're just inside of the.
This is the scale. I mean, O6 comes from gas which is very low density. It's a requirement in order for it to be highly ionized enough, so oxygen is not oxygen 405. So the largest scale is the scale of the gas at the density where there's O6.
So little RC of rho equals 50.
It's, yeah, 35 kiloparsec. Yeah, you're right. Yeah, exactly. Yeah, and the lower ions come from denser, which are smaller clouds. Yeah. Okay. So this is, instead of a projected view, this is just a mid-plane through the realization. Okay, so this gives you a sense of the volume filling factor of the different clouds. Okay, you can see that the volume filling factor drops very quickly with density. So the point is that the dense clouds, they have a large area filling factor. Okay, we actually observe them in several tens of % of sight lines. But in terms of the fraction of the volume that they occupy, it's a very small fraction. Okay. So one more interesting property is how stuff behaves as a function of distance from the galaxy center. This is the mean density of the cool baryons that we fit. You can see it's much lower than the dark matter density, and also it's flatter. Okay, so it's much less centrally peaked. In terms of the total mass, it's only 1% of the halo mass. So it's not a very significant baryon reservoir. It's roughly half the, or 30% of the mass of the disk. Okay, so that's roughly it. Two questions that come out of our work is first, what is the physical origin of the derived density structure? Okay, right? We have a range of 10 to the 4 in density. The temperature doesn't change. Okay, so the inner dense parts are overpressurized compared to their surroundings. Okay, so that means that they must expand. Okay, self-gravity is not strong enough to hold them in. So is that the radiation pressure, like I showed you in the first part of the talk. So something is causing these. Right, so if the dense clouds are expanding, that means that they need to be replenished with new material. So it's an interesting theoretical question to understand what gives this derived density structure. And also, the same methodology can be applied to other CGM samples at higher redshift and at lower galaxy luminosity. Yeah.
Questions over more?
It doesn't matter if these cluster or the galaxy being sampled is in a cluster or a field galaxy.
So that's a good question. This sample that we use is entirely field galaxies. I just talked to Howard Yee here, and he has a sample of the same absorption line measurements in galaxies in clusters. So it would be interesting to apply the same methodology to that and to see the differences, and then I can answer your question.
What about complement?
Yeah. So this this is mainly this sample is mainly disgalactic blue galaxies. There is a fraction of the sample which is red. What happens is that it appears that the O6 phase is missing in these red galaxies. Okay, so the lowest density phase appears to be missing from the red galaxies. This is something we're currently working on. It is missing. I mean,
Observationally, it's out there.
yeah, observation it's out there. It's less. I said it's less a strong result than I initially thought. But this is what we're currently working on. So why would the low density phase be missing in red galaxies and not in blue galaxies? I think that's an interesting question to answer. One idea we had is that if there's a more dense hot halo gas in the red galaxies, then that would create a pressure floor for this gas. Now this O6, it's 50 times the cosmic mean in density, and its temperature is only 30,000 K. So its pressure is very, very low. So maybe if there's like a pressure floor in the red galaxies, that doesn't let this phase exist. While in blue galaxies, no hot halo, so no pressure floor. Yeah, so that's just speculation, but it could be interesting.
So you mentioned in your first cartoon accretion and enrichment.
Yeah.
Did you say anything about that yet?
You didn't highlight that result.
Oh, yeah. Yeah.
High.
Yeah.
Crazy high.
Yeah.
Well, like clusters is worse than that.
Clusters is the third solar. But that's in the hot gas. The cold gas, there aren't too many absorption line studies in deep clusters, although just like power myself.
Yeah.
You do see cold gas in clusters, but it's really molecular gas way down in the center.
But still outside the disk.
Well, yes and no. Sometimes it's outside the disk. It's in a disk.
Okay.
In the BCG.
Ah, okay. Okay. Yeah. Yeah. It is very high density. It's a question if this reaches if it stops here at the CGM, it actually reaches the IGM, right? Which is not a question that we can answer yet.
So as you said, in this sample, they went up about 100 kiloparsecs.
100, yeah, 150. Yeah.
The L-star galaxies, the virial radius is 200, 220, 250. So this isn't even out to virial radiation. At high redshifts, it's sort of different, right? There you see these absorbers, you see more of them. And they go beyond the virial radius. And there they're pretty clearly associated with outflows. Here it's some mixture of inflow and outflow. But in the inflows are metal enriched.
Even if it's a field galaxy,
Yeah.
but if this is late time.
This is enriched to zero.
Yeah.
All right here.
Yeah.
So this is the CGM today. It kind of looks like this at higher redshift, but there's even more stuff out
That's like a petri dish.
Yeah.
But it isn't, I mean, this point about them probably being dynamical. Because there's no way to pressure confine this thing. And the sound crossing time isn't that long.
So it's turbulence.
It's, well, at least, it's not, probably isn't turbulent. So from his model, if you believe his model, which is basically just derived, actually, no, just from the observations, we did a little calculation on the board yesterday.
Yep.
It suggested that these things are basically spherical.
Yeah. 3D structures.
They're
Yeah.
not filamentary or not pressed. They're not compressed particularly.
Yeah.
Which was sort of surprising. But that doesn't sound like turbulence. Anyway, so
Yep.
unfortunately, John is leaving fairly early tonight, so unless people want to put together a really early dinner at 5 o'clock, we'll just have the snacks afterwards. So let's think, John.
Thank you.